So we're back to continue our look at linear independence in an abstract vector space. Again, let's remember here shows what we're talking about. If we have a set of vectors u1 through un, we form a linear combination of those vectors and set it equal to the zero vector. And if the only way that can be true is if all the scalars are zero, then the vectors are linearly independent. If there are non-zero scalars, at least some non-zero scalars, making that starred equation true, then our vectors are linearly dependent, and in that case we can solve for one in terms of the others. So this was the example we did before. We found that these three matrices were in fact linearly dependent, and so down here in the red box, we've written one of the matrices as a linear combination of the other two. So let's continue this. Let's take a look in the space P2. So let me put that here. That's, again, the polynomials of degree 2 or less. And so what we want to know in this case is whether these three polynomials, P1, P2, and P3, are linearly independent. So we set up the equation C1 times x squared plus 1 plus C2 times 3x minus 1 plus C3 times negative 4x plus 1. We set that equal to the zero polynomial, which is just the constant 0. Like before, we need to combine like terms. So we have C1 x squared. And then you can see that if we look for the x terms, we have a 3c2 times x, and we have a negative 4c3 times x. And then when we look at the constant term, we have c1 minus c2 plus c3. And we want that all equal to the zero vector. So what that means is we have this system of equations. C1 equals 0. 3c2 minus 4c3 equals 0. And c1 minus c2 plus c3 equals 0. If we set up the augmented matrix and row reduce it in this case, what we come up with is the matrix 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0. And remembering that this came from an augmented matrix where the columns represent the scalars C1, C2, C3, we see that the only solution is C1 equals 0, C2 equals 0, and C3 equals 0. So when that's the only solution, that then means that our system, or our vectors, which in this case are the three polynomials, P1, P2, and P3, are linearly independent. So let's conclude with that. P1, P2, P3 are linearly independent. For our next example, we'll go back to M22. And what I would do in this case is I would encourage you to just pause the video right now and determine for yourself whether you think these three matrices are linearly independent. And then when you're ready, push play again and see what happens here. Okay, so we're back, and if you set up the appropriate system of equations here in this case, and you augment the matrix, actually let me just show what the matrix is that you should get for your system. You should have gotten 1, 1, 2, 0, 2, 1, 1, 0, 3, 1, 4, 0, and 1, 1, 2, 0. Okay, and when you RRE REF this, what we get is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0. So again, this is the augmented matrix for a system. This will be C1, C2, C3 for your linear combination of those three matrices. You can see that C1, C2, and C3 are all equal to 0. So the matrices are linearly independent. I'm writing a fairly poor statement in the interest of time. It would be preferable to write out that the matrices are linearly independent. But let's move to the next example to keep things moving along. So this is our final example. We're back in P2, the set of polynomials of degree at most 2. And again, we set up a system of equations. And once more, let me encourage you to pause the video, try setting that up yourself, and see how things come out. As soon as you decide whether they're independent or not, go ahead and hit play again, and we'll see how that came out before trying this second question of giving P1 as a linear combination of P2 and P3. So go ahead and pause now and figure out whether they're independent. Okay, so to determine whether those polynomials are independent, we set up this vector equation, or really it's a polynomial equation. And when we group like terms, what we see is that C1 minus 2C2 plus 4C3 times x squared. For our x term, we get plus 2C1 plus C2 plus 3C3. It's the x term, and then the constant term looks like 3C1 plus C2 plus 5C3, and that's equal to 0. So our system of equations is C1 minus 2C2 plus 4C3 equals 0, 2C1 plus C2 plus 3C3 equals 0, 3C1 plus C2 plus 5C3 equals 0. When we RREF that, we end up getting this result: 1, 0, 2, 0, 0, 1, negative 1, 0, and 0, 0, 0, 0. So we can see in this case that C3 is a free variable, so I'll let C3 equal t. And if C3 was t, then we'd see that C2 would be t also, and C1 is negative 2t. And again, if t was 0, we'd have a solution, but we knew that to begin with. What we're trying to do is find a non-zero solution. So letting t equal 1, what we can see is that we would have the equation. Let's go back up here. Let me box in red the key equation that we were using, and let me note that this first guy, let's do this in black. So this thing is P1, this was P2, and this was P3. So what we have is if t was 1, we'd have negative 2P1 plus P2 plus P3 equals 0. And so that shows us, or that shows the linear dependence. Now remember, the next question was to solve for P1 in terms of P2 and P3. So I was going to have you pause and try that, but it should be pretty clear what happens. I'm going to move the P1 term over to the right side. So we have P2 plus P3 equals 2P1, which gives us then that P1 should equal 1/2 P2 plus 1/2 P3. And let's check that to see if in fact it's correct. All right, so let's see, let's just take 1/2. P2, let me remind you, was, let's see, P2 was -2 x squared plus x plus 1. And then P3, let's take half of P3. So what I'm doing is computing 1/2 P2 plus 1/2 P3 to see if it does in fact equal P1. So P3 was 4x squared plus 3x plus 5, okay, equals. So when I distribute the 1/2, we've got -x squared plus 1/2 x plus 1/2. And we add that to 2x squared plus 3/2 x plus 5/2, which equals, then we have x squared plus 2x plus 5/2 plus 1/2 is 6/2, which is 3. So we get x squared plus 2x plus 3, which is in fact P1 of x. Okay, so this part here, I should have said this is beginning here, this would be 1/2 P2 of x plus 1/2 P3 of x equals this. Okay, so that was rather poorly shown on my part. I should have started with this quantity here and then showed that it equals this, which in turn equals this, which equals this, which is in fact P1 of x. So we have then shown that P1 can be represented as a linear combination of P2 and P3. And that concludes our second video and last video on linear dependence and independence.